Good morning. Welcome back. Hope everything's going all right. For today, for attendance, I might be a little late on posting it, but I'll get the. I think there's a different check-in form for the remote learning days, so you can let me know that you're sort of present for the day by filling out the check-in form when you get in. That's part of your assignment, I guess. And then for this week, I'm going to be giving you a couple of assignments. I'll be posting video explanations for those. And this is your first one. So this one's going to be short because I wasn't realizing basically that one of you switched to I think Coda to first period. So I'm throwing this together real quick for you. So if you can see my screen, we were dealing with the normal distribution before we went on break. That basically described if you have a population, let's say you're talking about all the trees in Sterling. You have some population. Maybe that's your population. So that you have a lot of trees, a lot of different cases in that population. And let's say there's some average height. If you could find the height of every single tree in Sterling and measure its height, you could plot those like on a dot plot, and it would come out maybe looking something like a normal distribution, where there's an average value, and the probability that you'll find a tree near the average value is high if you pull one at random. So they're all kind of clustered, their heights are all kind of clustered around some average height. But as you move away from that height, as you go to tall trees or short trees from that average value, the likelihood of finding a very short tree or a very tall tree drops off. So there's fewer taller trees, fewer shorter trees. Mostly they're all clustered near this average height, maybe, let's say. Maybe this is adult trees, so like for mature trees of a certain type in Sterling, what's the average height? Most of them would be near some average height for their species, but there might be some freakishly tall ones, and there might be some freakishly short ones, just depending on their circumstances. And that's what the normal distribution sort of represented, was a distribution of the values of some variable, maybe height, weight, of some population. So this represents a population's distribution of values for some variable. What you need to describe a population like this is you need a mean. So let's say the mean is 80 something. I don't know what units we're using. And then there's a standard deviation, maybe 15. Now if you do that, you can see that the center of the distribution is at 80. That's spot on. Right in the middle. One standard deviation, that's 15 units below that. You have a z-score of -1, but that would be at 65 units. You have those trees. One standard deviation above, that'd be 95 units. There's so if I go to there, or if I get about 1, about 84% of the trees would be less than that height, whereas about 16% would be taller than that height if they matched a normal distribution. But you can program your normal distribution with just two numbers, the average value, if you know that, and the standard deviation. And then you were able to use the normal CDF to pick a value, and then you can know the probability of finding a tree, if you picked one at random, that was less than that value or greater than that value, using that normal distribution model to model your population. So hopefully that rings a bell a little bit. the only difference that we're going to talk about starting now is we're no longer going to be talking about pulling a single tree from the population and finding the probability that it's this height or that height. We're now going to talk about samples, because what we're moving into is called inferential statistics, and that is when you want to know something about an entire population. I want to know something about all the trees in Sterling. In that case, it's almost never the case that you're going to find every single tree and measure the height of every single one and then average them all. So there is an average value for all the trees in Sterling, but no one knows it, and no one's going to try to know it exactly. It's too much work, and it's too expensive in terms of either labor or time or even effort. No one wants to do that. But I still want to know something about all the trees in Sterling. Well, you can't know anything precisely unless you measure everything. But you can know things to a certain level of confidence using only limited information. So if I pulled, let's say, 10 trees at random, or 100 trees at random, and not all of them, just a sample, then I could use that sample if I believe it's a representative sample, if I believe that they've been chosen at random and this should be somewhat like the population at large, then I can actually use information about a sample to infer something about the entire population. So statistics is all about using a limited amount of information from a limited number of cases in a population and trying to extrapolate from that something about the whole population. Now, what you'll be able to do is say, not that, okay, I think the average value for all the trees in Sterling is 80. You'll never be able to say something like that with certainty. What you will be able to say is that, well, I'm 90% confident that the average value of all the trees in Sterling is somewhere between 70 and 85. I have 90% confidence that the value lies in that range. So that's what statistics can do. Now, what does that mean? What's the difference? Well, you're not certain. You just have a chance of being right. And if you're 90% confident and you've done it right, then basically what that means is that if you did this 100 different times, then 90 times out of those 100 times, you would be right. Statistics would lead you to the right answer. But if you did it 100 times and you were 90% confident that the value lied in your interval, that means 10% of the time, 10 times out of 100, this method will lead you wrong. This will give you the wrong answer 10 times out of 100. But 90 times out of 100, it'll be correct. So this isn't really about being right, necessarily. It's not about making the perfect decision. It's about making better decisions. And it's really useful when you repeat something over and over again, because you win some and you lose some. But if you win 90% of them and you lose 10% of them, you average out to being a pretty good winner. So that's what this kind of statistics can help you with, is making good bets. That doesn't mean you're making a good bet guarantees you to win. There's luck, there's improbable events that happen all the time. Life itself the evolution of life is probably an improbable event, and we're all here. So it happens. But this is going with the probable events. So if things are when you pull a sample and you do it properly, it's improbable that the sample will be super unrepresentative. It's more probable that the sample is pretty representative if the population follows a normal distribution. Whoops. That's what this is about. Now, the only difference when you're taking not one tree from the population, when you're taking, let's say, 100 trees from the population, you construct a normal distribution just like this, but the normal distribution no longer represents the population values. It represents something a little bit more complicated, which is the distribution of all hypothetically possible samples of size 100 that you could make from the population. So of all the trees in Sterling, every conceivable group of 100 that I could make, I could take this 100 set of trees, or this 100 set of trees, or some from each of those sets and make a different set of 100. For every conceivable set of 100 trees that I could assemble, if I found not the height of any individual tree, but the average height of that set of 100, then we create something that's called a sampling distribution. It's another normal distribution, but it doesn't represent the population heights. It represents the average height of every conceivable sample of 100 trees. So the basic idea here is that I'll have to explain a bit more about this, and I'll do that in another video I'll post tonight probably. But here we're just going over what's called a sampling distribution, and the sampling distribution, it turns out that to create a sampling distribution, if you know something about the population, isn't that hard. So even though you're not collecting every possible set of 100 trees, you know that if the population follows a normal distribution, then the distribution of all possible sets of 100 trees, that distribution, you can know things about its mathematical shape, knowing something about the population based on probability. Let's say that that all the trees in Sterling had an average height of 80 units. Well, it's kind of like flipping a coin. If I flip a coin, what's the likelihood that I'll get heads? Well, it's let's say heads represents a 1 and tails represents a -1. So if I flip it once, what's the probability that I'll get a 1 heads? Well, it's 50%. What if I flip it twice? What's the probability that I'll get an average value of 1 if I average the two values I get? Well, that means I'd have to get heads twice, and that'd be a half times a half. That'd be a quarter. I'd have a 25% chance of getting that. What's the probability that I would get an average value of 1 if I flipped it 3 times? An eighth, or 12.5%. So, because the idea is that if you flip the coin a lot, let's say 100 times, the most likely outcome is that you'll have 50 heads and 50 tails. It may not be exactly 50-50, but it's going to be much closer to 50-50 than if I flipped the coin 3 times, or 4 times, or 5 times. If I flip it 100 times, or 1,000 times, or 1,000,000 times, it's going to get much, much closer, the average, to 50-50, which shows that that the two sides of the coin are equally probable. So if you do it a lot, it's very hard for the average value to be anything very far from 0. Because it's very unlikely that I'll get heads. You know, if I flip it 100 times, it's unlikely that I'll get heads 70 times and tails only 30. That would not make sense given that they're equally probable. Likewise, if I have trees that are distributed according to this normal distribution, so that the average is 80, they're all clustered around there, and it's symmetrical. If I pull trees at random, I'm just as likely to pull tall trees on the right side as I am to pull trees on the left side, the short trees. It's equally likely to get a tall tree versus a short tree. It's just like flipping a coin. So if I take 100 trees or 1,000 trees as my sample, the idea that the average for that sample is going to be very far from 80, the true average, is highly unlikely. It's highly unlikely that if I picked 80 trees, they would all be on the tall side, unless I didn't pick properly, if I didn't do it truly randomly. But if my process of picking them is truly random, then it says I'm as likely to get ones on the right side as I am on the left side. So their differences from 80 should average out. So it turns out that as you take sample sizes, larger and larger sample sizes, the average value, the distribution of the possible average values that you could get tight. They get very close to the true average. So when I take what's called a sampling distribution, what's the distribution of all the possible samples of size 100 of trees in Stirling? What's the distribution of average heights? They are very clustered around the true average. It's very difficult to get 100 trees that average to 90 units if I have 100 of them, because all those differences are going to average out, just like flipping the coins. With this calculator, if I put in 100, you can kind of see what happens. The standard deviation is no longer 15 units, but it's now 1.5 units. So whereas before, when I took a sample size of 1, if I went to, let's say 81.5, so I go to that value, the probability of getting something less than 81.5 is 54%. So there's plenty of things taller, plenty of individual trees that are taller than 81.5 when the average is 80. But if I take a sample of size 100, the idea that they're going to average out to be taller than 81.5, I think I did the wrong value. Let's see, 81.5. Yeah, the probability that they'll be taller, I guess I should say, is 46%. So almost 50. It's not hard to find a tree that's taller than 81.5 units when the average is 80 and the standard deviation is 15. But if I took 100 trees at random and I averaged their heights, what's the probability that they will average to be taller than 81.5? Well, now it's only 16% likely that I'll get that. And that's because this shape doesn't show it, but you can kind of tell from the way this number line changes that the distribution, when you take a sampling distribution rather than a population distribution, it gets very tight around the same average. So it's still centered at 80, but the standard deviation, which instead of making it kind of wider, it gets tighter. And the way you do that is with let's see if I can pull up Writer. And I'll insert a formula. So normally in a normal distribution, you just need the average value, and you need the standard deviation. That's how you get a That's how you make a population distribution. To make the sampling distribution, let's say for sample of size 100, all you have to do is you do the same thing. You just put in your average value, because the sampling distribution are the same average value as the population. But instead of using the standard deviation for the population, you take that standard deviation and you divide it by the square root of the sample size. So, I don't know why there's parentheses there. I guess I should use brackets. So I would divide it by 10, because I'd take 100. The square root of that is 10. So if my standard deviation was 15, that would now become 1.5 as my standard deviation. That's what I'd use. So this calculator allows you to put in the sample size, and it will do that for you. But you could do it on your calculator as long as you just took this and divided by the square root of 100, or divided by 10. This won't let me do that, but that would make it 1.5. My numlock isn't on. That'd make it 1.5, and if I update that, that creates this effect. So if you're using a calculator, if you're using my calculator, you can leave this as the population standard deviation and just put in your sample size here. But if you're using your TI-84, I believe you should, it doesn't tell you the sample size, it'll let you enter that. So you would divide your standard deviation, and you can just type it, divided by the square root of, I can't do square root symbol, but you can, on your calculator, do divide by the square root of 100. That'll change this to 1.5. Your calculator should do that automatically. And that's how you create a sampling distribution on your calculator. And so you can do the normal CDF, you can do the inverse CDF, just like how you did before, before break. So you might need some refresher on that. If you struggle remembering that sort of thing, that for today, that's okay. Just do your best and try to just jog your memory, I guess. But the topic we're moving on to now is, we're not dealing with pulling an individual tree from a population where we'd use our normal distribution like regular. We're now talking about taking lots of them and creating a sample, and then creating a new distribution, not for pulling individual trees and calculating those probabilities, but for pulling samples of trees and finding the probability of their average value, not an individual value, but the average of all 100. What's the probability that they will average to this height or less, or this height or more? Otherwise, it's the same as we were doing before. You just have to adapt your standard deviation by dividing by the square root of the sample size. Now, just quickly, I will mention that sometimes they'll use this symbol for the standard deviation. Sometimes they'll use this symbol. The same thing. For the sample distribution, sometimes they will use this symbol. So it's the standard deviation of the sample mean. So it's not a value, it's the average value. That represents this. So it's the standard deviation of sample means, they'll call it. And they also have a name for it called the standard error, which I usually write SE. So the standard error is the population standard distribution, standard deviation, divided by the square root of whatever your sample size is. That's how you adapt your normal distribution to work for samples, and that's really the only change you got to make. Otherwise, you just do normal CDF and inverse CDF like you did before. So again, I know it's going to take some warming up to get used to how to do that again, but that's just the first, how to do it, how to make calculations for samples. I have a lot more I kind of want to go over, and I'll get another video up tonight explaining more of how this works conceptually, I guess, and where we'll be going for the next few days, this week and next week. So hopefully that makes some sense. I'll try to clarify a little bit more in the next videos. I just wanted to make sure I got this to you today. Anyway, good luck with trying to make sense of that. I'm going to post an assignment on MyOpenMath when I get the chance a little bit later in first period. But yeah, and if you have any questions, pop in during office hours after classes with a Google Meet, and we can talk more about it, or I could help you with questions. Anyway, have a great day today. Welcome back, and hope everything's going all right. Take care.